As we're wrapping up here, we're getting close to our final speakers here. I want to welcome up Mark Ciotola, who is with Sustainspace. He's a lecturer at San Francisco State University, has worked at NASA Ames and numerous other organizations, and now with Sustainspace, he received the 2017 Astrosat and Huntsville Prize, and I believe he's associated with the Hudson Alpha program down in Huntsville, Alabama, which I'm a big fan of. So I'll turn it over to you now, Mark.
Okay, thank you. So I admit this is going to be a somewhat dry presentation, but the implications of what will be covered could literally make or break space ag. Also, before I begin, it's important to distinguish between developing, building plant growth hardware versus changing, improving plants for use in space on Earth. They're both very important, both essential. However, this presentation focuses on changing and improving plants. So astroculture research can discover new valuable genes when plants behave differently in space. Often plants exhibit inheritable exotic gene expressions in the space environment. Some of these genes and expressions are useful or valuable for use in space and on Earth. So let's have a little bit of fun right now. Let's do some projections. In addition to feeding people in space, spaceplant R&D can provide major advances for Earth agriculture. That's already an existing multi-trillion-dollar market. But providing food in space is potentially, hypothetically, an even bigger market. People eat about 2 kilograms of food per day. So let's translate that into launch costs. So launch costs alone are roughly about $1,000 per kg to get food up into low orbit. So if you have someone like on ISS, that'd be about $60,000 per month per person. And that's just the launch costs. These are rough figures, by the way. So it costs about $10,000 to go to near deep space or the moon, which is about $500,000 per person per month. So if you want to go to Mars, yes. I'm getting a little bit of echo too. Okay, so for $100,000 launch costs for Mars, that's about $6 million per person per month. So literally, if you want to send a 20-month mission to Mars for a crew of 4, that's going to be about $500 million just for the launch to food up with them. So let's talk about Elon Musk. He's once put 1 million people on Mars. So the annual food launch cost would be $70 trillion per year, which is about 3 times the entire domestic gross product of the USA. So you can see that some of these expenditures are getting quite absurd. So sustainable presence of humans in deep space isn't going to happen unless we create sufficient plant varieties and growth capability to feed those people in space. So, however, there's a number of challenges which limit the advancement of growing sufficient plants in space. Some of them have been covered earlier. I'll go over a few more. There's not much in the way of current facilities to grow plants in space. There's literally just a handful of plant growth chambers in low Earth orbit at the present time. That's not to criticize vendors. I'm sure they'd love to send up additional capacity. There's also very limited downward capability to bring down genetic materials from space to Earth for analysis and further development. Although there's cargo missions going up all the time, well, every few months to the International Space Station, only a few of them, like the Dragon, can actually come back down to Earth without burning up in the atmosphere. Also, scaling up new varieties of agriculture, once you've developed new varieties or genetic changes, is neither trivial or inexpensive. One needs to bring in larger players. We're talking like maybe millions of dollars to scale up some of these crops. There's also a cultural gap between necessary partners. Most commercial space folks don't really get agriculture, and most ag business folks don't really get astroculture. And here's something I try to keep on telling NASA, and there's some NASA people here who are believers in this, what I'm about to say, but there's others like your engineering mindset who aren't, and especially the people who write the NASA budgets. People can't eat rockets. So if you're going to go to Mars or have sustainability in deep space, it's going to require a lot of food. If you have people in space for a long time, it's going to require a lot of food. However, people can't eat rockets, even if they're really big rockets. So building these big giant rockets to put people into deep space without sufficient plant capability to feed them is literally pointless. Okay, so there's not much funding for agriculture. By the way, I'm not saying we should get rid of the big rockets. I'm saying we should put the infrastructure to feed the astronauts in space in addition to building the rockets, in case there are any congressional people out there. So there's not much public funding nor private investment for astroculture research, at least not in the United States. Also, astroculture experiments are typically run without a clear commercial goal. That's fine for publicly funded science research, but not for attracting private investment. Further, placing a valuation on future research is always challenging, especially for individual projects. So I'm going to talk about something called the Valley of Death that's been referred to earlier today. So the Tech Valley of Death was the gap between angel funding, some initial funding for product development, and then scaling the product up into the public market. And so there's often not sufficient revenue to keep on funding development and expansion and scaling of a project. That's what they're talking about. There's also a space ag Valley of Death, and that's where there's seed funding, for instance, for fundamental plant research, some for some hardware development, but then a lot of these projects are, again, meant to be pure research. They're not necessarily meant to be commercial projects. A lot of them are around Arabidopsis selenia. Certain benchmark species are great for research, but themselves aren't commercial products. And so there's a scarcity of projects and funding in between this kind of like seed funding for plant research and big and medium ag companies who want to take products that improve their plant varieties that can be put into the field literally on Earth and turned into a major crop. There's a gap there. So Sustainspace has some proposals and ideas that we're working on to help bridge this. We're proposing a portfolio approach to funding commercial space research that could sufficiently mitigate risk to attract larger investors. And we feel that a super farm would be a facility to enable a portfolio approach. Let's talk about those a little bit more. A portfolio approach involves creating a fund that invests in numerous projects and companies rather than just a one-off. Investment funds often use a portfolio approach for investing in early stage technologies. And this approach improves the odds of capturing major hits to cover losses on portfolio projects. Can we do a quick sound check? Are you hearing me? Okay.
Hearing you loud and clear, Mark.
Great. I'm just getting echo here. Okay, so this portfolio approach is important because just one or two projects in a portfolio might produce all the returns. So this approach allows you to have economies of scale, reduce per project overhead, improve profitability, and have a better chance of capturing those big hits. So as you can see, even increasing your amount of projects from like say 1 or 2 or 3 to even a relatively modest number, such as say 10 or 20, significantly reduces the ROI standard deviation risk so that you can have a better idea of what your profitability is going to be, or at least what your risk level is going to be. This isn't a hard and fast rule. Even in Earth research, this can vary, but this projection was taken looking at the University of California plant portfolio, just as an example of how the risk deviation decreases. So another concept is to increase the amount of space for plants in space. And that's literally have a whole dedicated rack on the space station, whatever is going to be up there in the future, that could handle a lot of different types of chambers and a lot of chambers. Have plug and play open standards, so any vendor could put some of these plant growth chambers in there, and they could rent them out, they could sell them, but there'd be the availability to do the types and quantities and variety of experiments and projects that would support the portfolio approach. So another thing that we're looking into is using recurrent selection. A lot of plant scientists, agriculture folks know that plants can be selected from an experimental population to see which individuals respond the most to the project goals. So you can take plants up into space, see which ones respond to what you're trying to achieve, and then take offspring from those plants and reproduce those and have like a generational increase. And with increased access to space, hopefully there is increasing access to space. That means that you'll be able to do these life cycles faster and actually have a recurrent approach. Right now, there really isn't quite enough access to do that. So the great thing about recurrent selection is it's an effect that works because you've already shown it. So that each additional generation has an expected has an expected increase in response rate to whatever you're trying to do. So this is a relatively low risk to boost ROI. For instance, if you can double the response of a plant to their condition and make it inheritable, in certain circumstances, that'd be worth twice as much as the original generation of plants. So this is a nice way to boost ROI. So some conclusions. In addition to potential markets for growing food in space, the $1 trillion terrestrial agriculture market provides a valuable blue ocean commercial opportunity for agriculture research. A portfolio approach could be used to attract investment to astroculture research by reducing risk concerning return of investment, increasing in-space plant growth capabilities, essentially making the funding for a super farm possible, and improving profitability by achieving economies of scale. Recurrent selection can be used as a lower risk means to further boost ROI. So as you can see, the possibilities for space ag are especially exciting, especially with approaches that allow for significant private investment. Thank you.